work at Covalent, and I'm going to start with a little background in centralized infra. Then I'm going to move on to a little bit of rundown for the Ethereum Wayback Machine, going over the block system producers, block result producers, Ethereum node operators. And then I'm going to get into how the Ethereum Wayback Machine can augment AI through training and instance. So, decentralized infrastructure continuously faces user issues where simply there wasn't a big enough group of people in order to run infrastructure and support these networks. Back in 2013, if we remember the various cycles, we had script coins using tech to incentivize hard computation problems. You can think folding at home with a token. In 2017, we saw the rise of token-incentivized sensor networks, think phone. With all these projects today, deepen where there's a demand side and a supply side creating the economy to fund the network-percent incentives. Today, we are seeing decentralized forms of compute where the trust guarantees are not as robust but sufficient for financial applications like on-demand AES, CDS system. So decentralized infra these days is accepted and can be blockchain adjacent, yet still incentivized, and there is a very robust ecosystem of operators supporting many projects. So the Ethereum Wayback Machine is a decentralized network sharding Ethereum data that would normally be handled by an archival node, but will see inconsistencies in data like from reorgs. The system allows for the retrieval of blockchain data piecemeal, not within the constraints of soon-to-be obsolete traditional archival infrastructure. In essence, it's highly available and performance infrastructure, providing long-term data availability and more. Besides third hand. In the light of the ever-decreasing transaction context data state, due to competing biases and further decreasing storage demands on Ethereum nodes, like transient storage of log storage, yet ever-increasing data ordering complexity, EWM solves these issues. EWM consists of one initialist state chain, which is the Ethereum mainnet, a full EVM execution engine, obviously housing the staking contract to secure and emitting stable orders of the that's some operators. It collects delegations from operators, operational operators, two, permissionless document store, custom IPFS router node, operates across stack as centralized store of data artifacts, three, semi-permissioned print chain, the EWM print chain, which is a commit EFT tethered consensus S plus custom proof aggregation layer for attestations of off-chain computations like TX re-execution. Enables three storage models, EOA model score, validator attestation messages, UTXO model score, data structure, re-execution or aggregation messages, host REST SQL DB for storage proof verification over structured data to computation to proof requests. For fully permissioned message relayer, custom bridge for relaying messages across both chains, stateful long event processor and privileged actors for both chains, reward operators for state chain, for consensus proofs from respective operators on DWM proof chain. Post each step, these steps prove transactions comprising of hash of the data artifacts along with the IPFS CID, resulting from the off-chain computation over raw data is aggregated. This allows for redundant computation for these proofs that can be executed by operators in the system that have state delegated their respective operators. A validator operator pair PSOR on state chain that enables matching the appropriate actors. The data artifacts generated from such activity is also stored on local IPFS node or propagated to IPFS HTTP gateways. Consensus data artifacts with an on-state authority assumption received by validator or validated by approved chains are related to state chain for divvying up rewards for the respective actors that participate in creating them. The operator pipeline starts with the block specimen producer. So the export block specimen spec consists of three transaction types: withdraw, sender, state specimens, account read, storage, slot read, code read, universal, ADR no columnar, storage self-described specification for EVM. Down to direct live sync for any depth node as a fork with depth done by block specimen producers using client like EST-GET. State specimens export consists of all account state information, including nodes, balances, storage, slot, and code. This was accessed during the execution of transactions for that particular block. Each BSP object ranges from 0.5 to 1.25 megabytes in size. Raw RLP field export can be re-executed by ingestion of raw block specimens to create a one-to-one JSON RPC-like block responses with receipts. These are called block results. Later in the pipeline, BSP Geth, a fork of Go Ethereum, is used for exporting specimens. This is very computationally and storage heavy, has very computational requirements. There's also a client for stateless off-chain packaging, bundling, exporting, uploading of specimens run by operators, which has low computational overhead. Next in the pipeline, block specimens, which are fully concatenated bundles of blockchain data, are referenced by block result producers to create block results, which is important for later in the talk. Once all pre-state has been captured, the block result producers can pull in these files from IPFS using the CIDs from event logs posted on EVM proof chain for finalizing block specimen extraction events, and then can perform arbitrary transactions over any binary block specimen file concurrently. Block result producers are general purpose rule sets or plugins-based transformers for raw chain state data, and is written in Elixir to allow for soft fault tolerance and high concurrency throughput. This enables simultaneous data structuring with any client or consumer of data, slicing and dicing the data as they see fit. Such concurrent execution of Ethereum blocks via block specimens makes it possible to trace, enrich, or analyze blockchain data at an unprecedented rate with no sequential bottlenecks provided by block specimens. Block specimen is its own independent entity and available at a decentralized content address. This is stateless because it doesn't need to maintain the entire blockchain history to execute a block on the transactions in it. It executes the block ephemerally. But how? We capture the state specimens in an array for all accounts with their respective pre-state before execution. Then we take the transactions in that block and reconstruct them using the sender field from the block specimen. Finally, it takes the EVM and reconstructs the chain config from block specimen fields. Finally, statelessly, execute the transactions against the pre-state config and TX, aka block,
executing the pre-state along with the TXs to get the roots for all the tries and TX data, TX receipts. State root, TX root, receipts, FN, execute ephemerally, EVM, pre-state, TXs, etc. So the so-called block results are now ready to be uploaded to IPFS, and then a proof of the object is sent to EVM proof chain, from where any other application down the pipeline can pull and use according to their use case. So once we understand how the EVM or EWM works, we'll get into AI. These nodes operate aggregate, so query node operators, these nodes operate aggregate consensus block results from the last step at any point of interest to them. They start ingesting to form a comprehensive structured table of content for the block by block by block till where they would like to serve this data, requiring a fully independent hot local storage they can serve queries off of. Query node operators can then receive API requests that they fully submit, they fulfill submitting storage proofs to sequencers for the data they served. Storage proofs are stored on the EWM proof chain. So now we're going to get into incentives. It's important to understand that interactions in the EWM are being made constantly on two chains. In this image, for example, a simplified sequence is depicted where an operator adds themselves with an operator key pair to the staking contracts on Ethereum. If successful, the EWM bridge relays the message to the EWM proof chain and makes a TX in its state regarding the ID of the operator. This incremental, mononically increasing number is tracked in any interactions on either chains. Through successful log parsing and logging, the EWM bridge also maintains its own state of activities being undertaken, like with the example of the operator staking, meeting the criteria to become a block specimen producer. This message is relayed to EWM proof chain as a means to trigger an enabled state. This allows EWM proof chain to accept the create proof message from the operator en masse for every epoch. The logic of the EWM proof chain enables is to detect distinct sessions and all its contributing operator before finalizing a session. Once a session reaches a deadline and also achieves quorum, it is said to be finalized. The dual storages scheme of live versus finalized proofs make this process of finalizing a commit in the EWM proof chain history easy to retrieve and settle for rewards later on. In the send create proof cycle, multiple back and forth occurs between stake chain and EWM proof chain relayed by the bridge with messages initiated by the validator. With create proof, a message with chain ID of the underlying network source chain data object, the type of proof being specimen or result, the block hash, and the block hash, and the proof of the block hash, which is a SHA-256 of the content, along with the content address of the decentralized storage object is made to proof chain. This starts a proof session with a distinct proof session ID. Now the sessions have automatic deadlines, so EWM proof chain waits for multiple sessions from other operator which would have the same proof commit params. Note we can use ZKG commits to erasure coded block specimen data as well. Once minimum submissions from all available enabled operators is dynamically determined along for the qualifying quorum of submissions with some prior settled threshold, say 66%. All of the participants for a given session are aggregated by chain ID proof type and a validator ID, and the queried by the bridge for a reward validator TX on the stake chain is this transaction can dynamically take all the validator ID and the amounts that should be rewarded to them over an epoch. Finally, the operator can make a call to redeem the available rewards that have been unlocked on the stake chain or stake contracts with respect to their amount staked and work achieving consensus on the EWM proof chain. The EWM is built to perform a multitude of data structuring on blockchain data, fixing the garbage in, garbage out problem. The EWM is built for generalized data structuring and processing, including data aggregation, data restructuring, data repackaging, data inference, data indexing, data handling, data multidimensional semantic slicing, data validation, and others. So why not training and inference for an AI, and crypto's 100x growth? AI is hungry, RPC doesn't satisfy. Lack of verifiable data, the biggest problems are lack of verifiable data structures. Covalent modular data infrastructure helps create verifiable structured data sets essential for training effective AI models. Evolving technology is another issue. So blockchain data evolves with reorgs yielding false concept drifts or data drift signals. Covalent ensures consistency and reliability. Oh, I'm missing a slide. So I'm just going to say it out loud. So the EWM is modular data infrastructure solving verifiability in generative AI systems. And that's what's crucial here. So here's the EWM structure again. I promise it'll be real quick on this one, but in the context of AI. So block specimen producers collects raw data from blockchain, validates its integrity, and ensures that it is not tampered with. It's integral to the initial data handling, concatenates raw data from blockchains, ensuring accuracy and completeness, which we talked about, verifies data integrity, maintaining authenticity and verifiability, foundations for verifiable compute and accurate data streams for AI model training on blockchain use cases. Block result producers collects data from block specimens, which we talked about, specimen producers, and restructures it based on a specific use case. This structuring involves normalization, slicing, or scaling, I should say, aggregation and cleaning, making sure the data in the block result producer is ready for training without further data processing. The query node operator handles querying structured data and passes the information into the LLM sitting on top. If it is not possible in the block results producer, it uses another LLM to create a custom inference logic for the given prompt and will query the EWM proof chain to extract the relevant information. It then passes to the LLM sitting on top of the query node operator to provide a context-relevant answer to a given prompt. So the block result producer makes blockchain data ready for training. It already does this. It's already live. So some of the things that it can do, as we're seeing, is it does data normalization. It can do data normalization. Normalization involves converting data into consistent format removing inconsistencies and redundancies. This process ensures different data types that are compatible and can be accurately processed. A common normalization technique is min-max normalization, which transforms a feature into a range. Normalization eliminates variations that could skew the model's performance, ensuring all features contribute equally to the model training process. Data scaling. Scaling adjusts the range of values to ensure all features contribute equally to the model training process. It prevents any single feature from disproportionately influencing the model. Z-score normalization is commonly used where a feature is transformed. Proper scaling is crucial to avoid overfitting and ensures the model learns uniformly from all features. Data encoding. For categorical data, the block results producer uses encoding techniques to transform categories into numerical formats. This step is essential for incorporating non-numeric data into AI models. One-hot encoding is a popular technique where categorical values are converted into binary vectors, and encoding allows models to perform and learn from diverse data set types, facilitating the incorporation of categorical information. Data aggregation. Aggregation combines data from multiple sources, blocks, or transactions to provide a comprehensive data set. This holistic view is vital for creating robust AI models. Aggregation can involve summing, averaging, or concatenating data points to provide meaningful insights and patterns. Aggregation helps in offering a holistic view of data, enabling the training of more accurate and generalized AI models. NLP tokenization. In natural language processing, NLP tasks tokenization breaks down into text into individual units such as words or subwords that the model can process. Tokenization can be done using techniques like byte pair encoding, BPE, or word tokenization. Tokenization helps convert raw text into a structured format that feeds into NLP models, enabling them to process textual data effectively. And creating image embeddings. So for applications involving visual data, block result producers store generated image embedding, which are fixed size numerical vectors created by neural networks to capture essential features of images. Techniques like convolutional neural networks, CNNs, are used to create image embeddings. These image embeddings enable models to learn from and make predictions based on visual data, broadening the scope of AI applications. 2 more slides. So what about augmented inference? Or what about AI inference? So the augmented inference pipeline is essentially a RAG pipeline. So what is RAG? Retrieval augmented generation refers to AI models generating context-relevant responses by leveraging a combination of pre-existing structured data and dynamic querying techniques that leverage other AI models to create custom query extensions logic to query the data. Query node operators are company-operated modular data infrastructures, and this is key, infrastructure for specific LLMs or structured data use cases. There are three ways that can be done. So the QNO, query node operator, can leverage GPTs, LLMs that live on top to extract information from correctly structured block results from EWM proof chain. Once retrieved, the LLM can be another GPT, also on the query node operator, can generate an answer. Another option are the query node operators leveraging a trained AI model that again lives on top of the QNO for specific use case like price prediction, anomaly detection, etc. This model can only take a specific format of data to generate predictions. If that file is present in the block results, it uses it to create predictions by passing the upcoming data into the trained AI model. Q&O uses AI to create a custom data extraction. This is the third way it can do it. For the block results producer to extract the data from the EWM proof chain block specimens and make it available for inference via a block result. This may require additional implementations to the block result producer, but it is very possible. So AI is biased, Ethereum is not. The future relies on verifiable, decentralized infrastructure. So thank you for coming to my talk.